Okay, think about the batteries powering pretty much everything right now. Your phone, laptop, maybe even your car if you've got an EV. They're all running on lithium ion.
And they're great. They've gotten us this far, but they're kind of hitting their limit performance-wise.
Totally. It feels like we're bumping up against a ceiling.
Yeah.
So if today's Li-ion batteries are like Iron Man's first suit, the Mark 1,
Yeah.
what we're really chasing is like the Mark 85, the endgame suit. And that means pure metal anodes.
Exactly. That Mark 85 level, it's,
Okay.
it's a game changer. We're talking energy densities that just blow the current ceiling away.
How big a difference are we talking? Well, think about this. Conventional ion with the graphite anode, they max out around, say, 300 watt hours per kilogram, give or take. Okay, 300, got it.
Now, swap that graphite out for pure lithium metal. The potential density, even in actual working pouch cells, not just theory, could jump up towards 710 watt-hours per kilogram.
Wow, okay.
Great.
That's more than double. That's huge.
It is, and that's why researchers are kind of obsessed with using pure metals.
But like we see in every superhero movie, right? With great power comes, yeah, well, usually chaos if you can't control it.
Yeah, precisely. And that chaos, that difficulty in control is exactly what we're diving into today. How do we actually unlock this next generation of energy storage? And why are these amazing high-energy metals such a headache?
Yeah, what's the catch?
So our guide for this deep dive is this fantastic, really comprehensive review paper. It was published in the journal Science.
Science, okay, top tier, definitely. And the title lays it out. The contrast between monovalent and multivalent metal battery anodes, it really maps out the whole complex territory for us. And we should definitely give a shout out to the team behind this. The primary contributors were Yangjian Li, Sonal Kumar, and Asko Liang Yang.
Yeah, and the corresponding authors, Jun Lu, Yan Yao, Kisi Kong, and Ziwei Sei. It's a big international collaboration. You got folks from A-Star in Singapore, Zhejiang University, University of Houston, Seoul National University. Really a global effort.
Impressive. So they laid out a framework you mentioned.
Yes, a really crucial distinction. They split these next-gen metals into two main families based on their chemistry.
Okay, family number 1.
The monovalents. These are the ions that carry a single positive charge. Think lithium, Li+, sodium, Na+, and potassium, K+.
Gotcha. Single charge. What's their deal?
Super high capacity, generally speaking, and very negative electrochemical potentials, which is good for voltage. They're the highly reactive high-energy crowd.
All right, so that's group 1. What's group 2?
Group 2 are the multivalents. These guys carry more punch 2 or even 3 positive charges. We're talking magnesium, Mg at 2+, calcium Cat 2+, and aluminum Al3+.
Okay, so more charge per ion. What are their advantages?
Well, first off, they're way more abundant in the Earth's crust. Think about aluminum versus lithium, a huge difference in availability and cost.
That's a big deal for scaling up, right? Resource concerns.
Absolutely. And beyond abundance, they often pack a punch in terms of volumetric capacity, how much energy you can cram into a given space.
Oh, interesting. So like for smaller devices?
Exactly. Yeah. If you need a really compact battery, aluminum is kind of a star. Its theoretical volumetric capacity is like 8046 milliamp hours per cubic centimeter. Yeah. Compare that to lithium's 2062.
Wow, okay. Almost 4 times denser energy storage by volume. That's significant.
It really is. But, and here's the big but, both families, the monovalents and the multivalents, they face these two massive, potentially battery-killing problems.
Ah, the headaches arrive. Problem number 1. Problem number 1 is very visual, very dramatic. The dendrite monster. This is basically a mechanical failure mode. Dendrites, I've heard that term. Sounds bad. Like something growing where it shouldn't.
Precisely. When you charge one of these metal batteries, you're essentially plating the metal ions back onto the anode surface. Ideally, it should lay down nice and smooth like paving a road.
Okay, makes sense.
But the universal problem is none of these metals really like to do that. They deposit unevenly, irregularly, and this uneven growth causes all sorts of issues.
Like what? Just making the battery lumpy?
Worse. It leads to losing active material, so your capacity fades. But the really critical issue, the safety hazard, is when these irregular growths form sharp spikes or filaments.
Spikes? Those are the dendrites.
Those are the dendrites. And if they grow long enough, they can actually punch right through the thin separator membrane that keeps the positive and negative sides of the battery apart.
Ooh, that sounds bad, like crossing the streams in Ghostbusters.
Yeah, exactly like crossing the streams. You get an internal short circuit, and that can lead to overheating, thermal runaway, fire. That's the big fear with metal anodes.
Yikes. Okay, so dendrites are bad news for all these metals. Do they grow the same way for both families?
No. And this is a key difference. The monovalent metals, lithium, sodium, potassium, they tend to grow these really aggressive, nasty shapes. The paper calls them whisker-like, moss-like, and tree-like dendrites.
Tree-like little metal trees growing inside my battery.
Pretty much. They branch out, they reach far. Think of them as the vicious vines, just snaking their way towards that separator, ready to cause trouble.
Okay, vicious vines for the monovalents? What about the multivalents? Magnesium, aluminum.
They behave differently. Their growth is usually less dramatic. Because they have higher surface energies, different crystal structures like magnesium is hexagonal close-packed, lithium is body-centered cubic form. They tend to form things like interconnected platelets and random fibers or spheres.
Platelets and spheres? Sounds less scary than trees and whiskers.
Generally, yes. They form denser deposits, often flatter overall. They're still irregular, mind you, it's not perfect. But they seem less prone to forming those really long, catastrophic dendrites that cause immediate shorts. We could call them the denser deposits.
Okay, so the failure mode is different. That's something, I guess. Any good news on the dendrite front? Did the research find anything surprising?
Actually, yes. There was this really cool bit about potassium, one of the monovalents. A kind of dendrite self-healing phenomenon.
Self-healing. Like Wolverine, the dendrites just disappear.
Sort of. What they found was, counterintuitively, if you increase the charging current density for potassium up to around 2 milliamps per square centimeter, the dendrites that had formed could actually smooth themselves out.
Wait, hang on. Increase the current. Usually we hear that faster charging makes dendrites worse. You're saying for potassium, hitting it harder makes it smoother, safer.
It sounds backward, I know.
Yeah.
But yeah, for potassium metal, it seems to work. The idea is that potassium atoms have a really low energy barrier for moving around on their own self-surface diffusion.
Okay.
So that higher current seems to give the atoms enough energy to quickly rearrange themselves, filling in the valleys and smoothing out the peaks of the dendrites. Lithium apparently needs a much, much higher current, like 9 mecamel, to see a similar effect, but potassium does it relatively easily.
Huh. So maybe we could use smart charging pulses tailored to the metal to kind of manage the dendrite growth.
That's exactly the implication. It suggests we might not have to eliminate dendrites entirely if we can control their shape and maybe even reverse them using the right charging strategy. It's a potential breakthrough for safety and lifespan.
Okay, that's fascinating. So managing the physical shape, the dendrites, is one major challenge. What was the second big problem you mentioned?
The second problem goes deeper, down to the chemical interface. It's the solid electrolyte interface, usually just called the SEI.
Yeah.
The SEI.
SEI, right, that layer that forms where the metal touches the liquid electrolyte.
Exactly. Forms spontaneously because these metals are so reactive, and you actually need it to form. A good SEI should let the metal ions, like Li+, pass through easily, but it must block electrons. If electrons get through, the battery just self-discharges.
So it's like a selective filter or a bouncer at a club. Ions get in, electrons stay out.
Perfect analogy.
Wow.
It's a necessary evil. But the kind of SEI that forms is dramatically different between our two metal families, and that causes opposite problems.
Okay, let's break that down. Start with the monovalents again, lithium, sodium, potassium. What does their SEI look like?
With monovalents, the single charge ion, like Lic+, floating in the electrolyte tends to be surrounded mostly by the solvent molecules. It's called a solvent-dominated solvation structure.
Okay, ions wrapped in solvent. What happens when that structure breaks down at the metal surface to form the SEI?
You end up with an SEI that's mostly made of decomposed solvent molecules, so it's organic rich. Think of it like maybe a layer of wet tissue paper.
Wet tissue paper? That doesn't sound very robust.
It's not. The good news is this organic-rich SEI usually lets the ions pass through pretty easily. So the kinetics are good, the battery can charge and discharge quickly.
But the bad news?
The bad news is it's mechanically weak. Remember, the metal anode expands and contracts a lot during charging and discharging. This flimsy organic SEI just cracks and breaks apart under that stress.
Ah, and when it cracks?
It exposes fresh reactive metal underneath. That fresh metal immediately reacts with more electrolyte, forming new SEI, consuming active lithium and electrolyte. It's a vicious cycle. The SEI is constantly being destroyed and reformed, which drains the battery's life over time. It's what the authors kind of call the organic mess. Okay, so for monovalents, the SEI is ion-friendly but structurally weak and unstable. It keeps breaking. Got it. Now flip to the multivalents magnesium, calcium, aluminum. They have that higher charge, right? 2+ or 3+.
Right.
And that higher charge density acts like a much stronger magnet, or like you said earlier, maybe a mini black hole. It pulls things in much more strongly.
What does it pull in? Not just the solvent.
Exactly. It pulls in the anions from the salt and the electrolyte much more tightly. Those negatively charged ions get incorporated directly into the ion's immediate neighborhood, its solvation sheath. This leads to an anion-participated solvation structure.
Okay, so the anions are getting involved directly. What kind of SEI does that create when it decomposes?
It creates an SEI that's rich in inorganic components, often derived from those anions, things like oxides, fluorides, chlorides, depending on the electrolyte.
Inorganic. That sounds tougher than the organic mess, like maybe a ceramic tile instead of wet tissue. It is generally much tougher mechanically. But here's the crippling problem. This inorganic-rich SEI formed by multivalents is often ion insulating. But the ions need to get through. The bouncer isn't just keeping electrons out, it's blocking the ions too.
Precisely. It forms this hard, dense, inorganic wall that completely passivates the anode. The ions hit this wall and just stop. The reaction grinds to a halt. You might have this amazing metal with incredible theoretical capacity, but if the ions can't move across the SEI, the battery is dead on arrival.
Wow, so it's a complete reversal of the problem. Monovalents have a weak SEI that lets ions through but breaks down. Multivalents form a tough SEI that doesn't break, but it blocks the ions.
You've got it. It's this fundamental paradox. Monovalents suffer from an SEI that's too permeable and fragile. Multivalents suffer from an SEI that's too impermeable and robust, at least to ions.
Man, batteries are complicated. So how do we fix these totally opposite problems? What are the solutions?
Well, this is where the real engineering comes in. The review highlights two main strategies that researchers are pursuing, and again, they often involve doing opposite things for the two families.
Okay, strategy one.
Strategy one is engineering the anode surface itself. If dendrites are caused by uneven plating, maybe we can guide the metal atoms to deposit more orderly.
Like telling the atoms where to sit down.
Kind of.
Yeah.
The goal is to create homogeneous and closely packed crystals on the anode surface, and ideally have those crystals oriented in very specific ways relative to the current collector.
Crystal orientations,
Oh,
like
yeah.
making sure all the bricks are lined up the same way.
Exactly. They talk about targeting specific crystallographic planes. For lithium, sodium, potassium, they want the 110 plane facing outwards. For magnesium, it's the 002 plane. For calcium and aluminum, maybe the 111 plane.
Why those specific numbers, like 002? Does that matter?
It matters hugely. That 002 plane, in magnesium, for example, represents the flattest, most stable surface at the atomic level. If you can force the magnesium to plate with that face exposed, it tends to deposit much more smoothly, resisting dendrite formation.
How do you force it? Can you just ask the atoms nicely?
Hey, not quite. This is where material science comes in. Researchers are using engineered substrates, like specific types of 2D materials called MZenes. These act like a template or a seed layer.
Ah, like laying down a foundation that encourages the right kind of crystal growth.
Precisely. The paper mentions using MZene films to get that desirable 002 textured magnesium. And the result? They observed pitless stripping and crack-free plating. That's the dream smooth deposition, smooth removal, leading to long cycle life.
Okay, so engineering the solid metal surface is one angle. What about the liquid part, the electrolyte? That's strategy two, smart electrolyte design. And again, we need opposite approaches. Remember the monovalence problem. Their SEI is too organic and weak, right? The organic mess needs to be tougher.
So the strategy is to make their SEI more inorganic.
Ow.
By forcing those electrolyte anions, which normally stay away, to get closer to the Li plus or Na plus ion before the SEI forms.
How do you force the anions closer?
Basically, you make the electrolyte incredibly salty. Use really high concentration electrolytes, or HCEs. We're talking concentrations of 3 molar or even higher. At such high salt levels, there simply aren't enough solvent molecules to go around, so the anions are forced into the ion's inner circle.
So you're drowning the lithium ion in salt to change its behavior.
That's a good way to think about it. Or, if HCEs are too expensive or viscous, researchers use a clever trick called localized high-concentration electrolytes, LHCEs. They add a non-polar diluent, like a special type of ether that doesn't dissolve the salt well. This creates pockets of high salt concentration locally around the ion, achieving a similar anion-rich structure without using quite as much salt overall. Okay, so for monovalents, more salt, more anions near the ion, leading to a tougher, more inorganic SEI.
Right.
What about the multivalents? They already have a tough inorganic SEI that blocks ion,
Right.
the inorganic wall. So for them, the strategy is the complete opposite. We need to break up that tight bond between the highly charged multivalent cation like Mg2+, and the anions. We need to make their SEI less inorganic, more organic, and more ion permeable.
How do you break that bond?
You use electrolyte solvents that are really good at grabbing onto the metal ions, strongly solvating solvents, things like DMAC are mentioned. These aggressive solvent molecules essentially muscle their way in, surrounding the Mg2 plus or Al3 plus ion and pushing the anions further away.
So you're using strong solvents to pry the cation and anions apart.
Exactly. This encourages the formation of an SEI that's derived more from the solvent, making it more organic rich, rather than the anions. The goal is to create an SEI that's still protective, but allows those Mg2 plus or Al3 plus ions to actually pass through, enabling the battery to work.
Wow, it really is fascinatingly opposite. Monovalents trying to build a stronger inorganic SEI using salt. Multivalents trying to create a more permeable organic-like SEI using strong solvents.
It's a beautiful example of tailoring the chemistry to the specific problem. And this reverse engineering approach extends even to directly modifying the SEI's chemical makeup.
How so? Like adding specific ingredients to the electrolyte.
Yeah, or creating artificial SEI layers before the battery's even assembled. For lithium, sodium, potassium, since they need mechanical toughness, researchers are adding things that form robust inorganic components like metal fluorides, LiF, NAF. These have wide GaN gaps, good electron insulation, and high stiffness.
Like adding ceramic reinforcement to the SEI?
Pretty much. Sometimes they pair these hard inorganic components with flexible polymers, like PVDF, creating a composite bilayer SEI, something that's both tough and can flex a bit with the metal's volume changes, like a flexible suit of armor.
Okay, armor for the monovalents. What about the multivalents, trying to get ions through their tough layer?
For them, the focus is on incorporating components that are inherently good ion conductors, even within that inorganic matrix. Things like magnesium hydride, MgH, or calcium hydride, KHX, are being explored.
Hydrides, hydrogen compounds.
Yeah, these can sometimes act as fast pathways for Mg2 plus or Ca2 plus ions to move through the SEI. It challenges the old view that all multivalent oxides or fluorides are total insulators. The structure and finding specific conductive phases within the SEI are key.
So it's about creating tiny highways for the ions to travel through the otherwise blocking wall.
That's a great way to put it. Finding or creating those conductive pathways is critical for making multivalent metal batteries work reversibly.
Okay, this is incredibly detailed science. Let's pull back a bit. What does all this mean for us, in the real world? Where will these different types of batteries actually end up being used, assuming we solve these challenges?
Well, the idea is to leverage their unique strength. Lithium metal, being the undisputed king of energy density by weight, is really targeted for premium applications where weight is critical.
Like electric airplanes, long-range EVs.
Exactly. Long-range electric vehicles, potentially electric aviation, anywhere you need the absolute maximum energy packed into the lightest possible battery.
Okay, that makes sense for lithium. What about the other monovalents, sodium and potassium? They're heavier, right?
They are heavier, but they are vastly cheaper and more abundant. So sodium metal and potassium metal batteries are prime candidates for large-scale stationary energy storage. Think grid storage.
Backing up solar farms and wind turbines, precisely. For grid storage, the upfront cost per kilowatt hour is often more important than weight or even volume. And sodium and potassium have another potential cost advantage. They might be compatible with cheaper aluminum current collectors instead of the expensive copper foil used in lithium-ion batteries. That could significantly lower the overall system cost.
Okay, cheap and abundant for the grid. Makes sense. Now, the multivalents magnesium, calcium, aluminum, where do they fit in?
They have a few potential niches. Because metals like magnesium and aluminum have much higher melting points than lithium or sodium, they might be better suited for applications that need to operate in extreme environments, particularly high temperatures.
Like over 100 degrees Celsius?
Potentially, yeah, think industrial processes, downhole drilling, maybe certain aerospace or military uses. Also remember, aluminum's high volumetric capacity. That makes multivalents attractive for applications where space is extremely tight, needing very compact packaging. And there's still hope for M&L being potentially safer due to that dendrite behavior. So different metals for different missions, essentially. Tailoring the battery to the job.
That's the core message. There's probably no single best metal anode. It's about matching the specific properties, energy density, cost, abundance, operating temperature, safety characteristics to the right application.
Okay, let's try and summarize the key takeaways from this deep dive based on that science review by Lee, Kumar, Yang, and the team. What's the first main point?
I'd say the first point is that unlocking these next-gen metal batteries requires Totally different, almost mirrored strategies for the monovalent family versus the multivalent family. Their fundamental chemistry, driven by that single versus multiple charge, dictates completely different problems and solutions, especially regarding the SEI.
Right. Opposite problems need opposite fixes. Okay, takeaway number 2.
The two central challenges are, one, controlling the physical shape of the metal deposit, managing those dendrites, the vicious fines versus the denser deposits, and two, chemically engineering that critical SEI layer. For monovalents, the goal is a tough, stable, often inorganic-rich SEI. For multivalents, the goal is creating an SEI that is actually ion-conducting, likely by incorporating organic or hydride components.
Got it. Control the shape, control the interface chemistry, but do it differently for each family. And the third takeaway.
The third is that success really depends on rational design across the board. It's not just about the metal. It's about tailoring the electrolytes, using high salt or specific solvents, and engineering the surfaces and interfaces, maybe with specific crystal textures or artificial layers, to perfectly match each metal's unique behavior. That's how we enable both super high-energy EVs and cost-effective grid storage.
So it's a whole system approach.
Absolutely, and the authors make a really interesting point near the end. They emphasize that these failure modes we've discussed, dendrite growth cracking the SEI, mechanical stress interacting with chemical reactions, they're really at the intersection of different fields.
Yeah.
Meaning it's not just electrochemistry anymore. They explicitly call for researchers from mechanical engineering and metallurgy to join forces with the electrochemists,
Yeah.
understanding stress, strain, fracture mechanics, crystal growth. These are becoming just as important as understanding electron transfer.
That's a great point. It leads perfectly into our final provocative thought for you, the listener. Given that creating these powerful new batteries seems to require controlling matter right down to the atomic crystal structure and designing materials that can withstand physical stress while performing complex chemistry, how much of the future of energy storage hinges not just on discovering new chemical recipes, but on fundamentally mastering materials science and mechanical engineering to build batteries that are more like finely tuned, self-healing machines?
Yeah, are we moving beyond just mixing chemicals to actually constructing materials atom by atom designed to handle these extreme conditions? It's a fascinating question for the future.